All right. So what we're going to be looking at tonight is the section 3.11. And what we're going to start out with is linearization. And the idea here is we're going to approximate a curve with a tangent line. So let's say we have the x value a right here, and we have L of x, and we have f of x. So the idea is this: when x is close to x equals a, then f of x is approximately L of x. So the idea is that if we zoom in to this part here, for all intents and purposes, ln x might be a good enough representation of f of x. That's the idea. So what we're going to do, we're going to construct L of x. And we're going to construct L of x in terms of the derivative of f of x. Because L of x is a tangent line, we can express its slope as a derivative of f of x. So first off, the slope of L of x was going to be f prime at x equals a, because L of x is tangent to f of x at x equals a. And then a point on this graph, well, L of x, if you recall, well, it's tangent to f of x at a and f of a. So the point a fa is on L of x. So to derive L of x, we're going to use our point slope formula. Where in this case, this is x1 and this is y1. You get y minus f of a is equal to f prime of a, x minus a. And then we're going to solve for y. Y is f of a plus f prime of a, x minus a. And so we're just going to call this y, because this is just the graph. This is just the line that is really L of x. Because L of x has the slope f prime, and it passes through these points. So we're just going to call L of x. And so that's going to be our L of x. So again, remember, L of x is tangent to f of x at x equals a. And again, so what this is saying for x near x equals a, f of x is approximately, it's close enough to L of x, which is, well, now we know what L of x is. So we're going to apply this, and we're going to apply it to a square root function here. And what we're going to see is that we're going to choose an a, and x equals a, and that the closer to x equals a we choose our x values, we're going to find that our approximation is more accurate, or there's less error. So for example, we'll find the linearization of f of x is the square root of 1 plus x near x equals 0. So we're going to approximate f of x near x equals 0. So first off, let's get f prime. We got to construct our L of x. So f prime will be 1/2 1 plus x to the, let's see, 1/2 minus 1, or 1/2 1 plus x to the minus 1/2, or 1/2 1 plus x to the 1/2, or 1/2 square root 1 plus x. So this is our f prime of x. So this is going to be part of our L of x. This is our slope. So if we compute f prime of 0, we'll get 1/2 times the square root 1 plus 0, or 1/2 root 1, or 1/2. So that's our f prime of a. It's going to be 1/2. Now we still need an f of a. So f of a will be f of 0, or the square root of 1 plus 0, or square root of 1, or 1. So now we can put this all together. L of x will be f prime, I'm sorry, f of a plus f prime of a x minus a, or 1 plus 1/2 x minus 0, or 1 plus 1/2 x. Or here, I'll write it out a little better. L of x, let's say 1/2 x plus 1. So what this is when x is close to 0, we can approximate the square root of 1 plus x using this line. So let's take a look at some approximations. So let's say we're going to say, let's say x is 0.2. Well, if we do that, f of 0.2, which will be the square root of 1 plus 0.2, or square root of 1.2, and that's approximately, I have to round it off, 1.002497. So this is our true value. Now let's try our approximation function, L of 0.2. Well, that's 1/2 times 0.2 plus 1. And that's going to come out to 1.1. Oh, I'm sorry, I looked at the wrong number. This is actually a different number. Let me back up. 0.95445. Apologize for that. So this is our true value. This is our approximation. So if we take the absolute value of the difference, what we'll get is an error of this amount. So this is how far off our approximation is. Now, let's take a value of x that's even closer to 0. Let's go with 0.005. And let's see if we can prove on this. So what I'll do, I'll write this down here. This is how far off the approximation was when the x is 0.2. That's the amount off. So let's go with this. Now, in this case, f of 0.005 or 5 thousandths will be 1 plus 0.005 or the square root of 1.005. And this is approximately, that was that other number, the 002497. So now let's take a look at our approximation. L of 5 thousandths. And when we calculate this, we're going to get this. So now if we take a look at the difference, or the magnitude of the difference, taking the absolute value of this difference, what we're going to get is a very small number. So what do we get from this? Well, when x is 0.2 or 2/10, this is how far off our approximation is, this number here. But when x is 5 thousandths, we're off only by this amount, a very tiny number. So what this basically says is the closer x is to x equals a, in this case, x is equal to 0, the smaller the difference between f of x and L of x. So when we do these approximations, it is going to matter if you start choosing x values very far away from x equals a. Your approximation is not going to be as good. So that is something to keep in mind. So that's one thing in this section they talk about. Now, the next thing they talk about are differentials. And what we're looking at is something in the effect df dx versus delta f over delta x. And what we're interested in is what is the difference. To abbreviate difference there. Now, there's one thing we do know about df, and this is going to come up later. But if df dx is f prime of x, well, we can write df as f prime of x dx, where delta f, and what we're going to do, we're going to let dx equal delta x. We're going to allow for that. So that being the case, is this the same as delta f? Is df and delta f, are those the same thing? So what we're going to do is we're going to construct a graph. And we're going to look at some properties here. And let's see if we can figure it out. We're going to be okay making this equivalence. And we know df can be written like this, but is this the same as that delta f? So let's find out. So again, we're going to let delta x be equal to f dx. Let's take a look at this. Where delta f and df, the same thing. So let's take a look at this. We're going to choose a second point here. There's this and this. This will be a plus dx, or a plus delta x, either way. So this is L of x, and this is f of x. So if we take a look at the points, this is L, and we have a plus delta x, because that's the x value here. And as you would guess, this is going to be f of a plus delta x. So there's your L, and there's your f at that location. Now here, L is tangent to f, so they're equal. So f of a equals L of a. So that's what we have there. Now, I'm going to call this x1, and I'm going to call this x2. And granted, I'm going to erase everything on here, but take a look at this in your notes. We're going to refer back to this a little bit. But we're going to look at the difference between, well, here, I'll put it in. This here is delta F. And then we're also going to look at the distance. Delta L. So you have delta F and delta L. And you'll see why this is going to be important, why we're going to compare these two distances. So first thing, let's just say what delta F is. So delta F is F of x2 minus F of x1, or F of a plus dx minus F of a. And again, dx could be delta x. So that's delta F. Now, what about delta L? So delta L is L of x2 minus L of x1. And what this is going to turn out to be L of x2. Now remember, x2 is L of a plus dx minus L of a. So L of a plus dx, well, it's going to be f of a, f prime of a rather, oh no, f of a, plus f prime of a times, and this is where we make the substitution, this is a plus dx minus a. Remember, for L of x, I'll write it to the side here, L of x near x is a is f of a plus f prime of a. Ooh, running out of room. Let me stretch down here. F of a plus f prime of a x minus a. So this is the approximation when we're near x is a. So what that's going to mean is that we're going to make our substitution. We put x plus dx here. I'm sorry, a plus dx here. A plus dx is going to be here. And that's what we've got. Minus, well, f of a plus f prime of a. Again, just following this. And then we substitute the a for x. And if we simplify this down, what we're going to get, and this might seem a bit surprising, is f prime of a dx. So delta L is f prime of a dx, while delta F is f of a plus dx minus f of a. So where is this getting us? So delta L is equal f prime of a dx, or delta L is going to be df dx times dx, where x equals a. And we're going to, again, letting dx be the same as delta x, the difference between those x1 and x2 points. Or what's going to happen, these are going to cancel. We'll get delta L is equal to df, where if you evaluate this at x equals a, and again, we have our dx is delta x. So what is this saying? Well, now df, and this is kind of the surprising thing, we know what delta f is. So df, where delta f is the change of the function f, df is the change of the linearization of f near x equals a. So what we end up getting is delta f is still the change of the function, but df is the change of the linearization near x equals a, because we compute the linearization near some x value. And again, if we move away from this, the accuracy of the linearization doesn't work. So what we're going to look at now, and you're going to kind of get a hint of what we're going to be doing from this, how these two cancel out if we rewrite this as df dx. So we're going to compute df, but what we're going to do, we're going to compute it using this form. We're going to do this. So for example, if f of x equals 3x squared minus 6, then f prime of x, well, this will be 6x minus, 0. So 6x, because derivative of a constant is always going to be 0. So we can rewrite this as df dx is equal to 6x. And the way you can think about this is multiply both sides by dx. You could think of it like this. When you do that, you get df is 6x dx. Though this formula is, keep that in mind. You'll do fine. But a trick you can think of it as multiplying both sides by dx. But this is the formula that it's getting us through. And so that's it. Computing a differential, we're not going to worry about figuring out delta L. We're going to worry by just using this. So that being said, you can rewrite all derivative formulas as differential formulas. So what this means, if we have, say, u plus v, these are two functions. The derivative of a sum is the sum of the derivatives. Well, what this is going to become is the differential of the sum of two functions will be the sum of the differentials. So another one that's going to come out, this is a little peculiar, I want to show you this one, is with the chain rule. So for the chain rule, and we want to keep in mind that df is f prime dx. I'm going to use that. I'll throw that in there. So for the chain rule, we have df of some function u dx is df du times du dx. And so what this is going to become, this here is going to be our f prime. That's right here. So what this will be, it'll become dfu df du times du. And again, the way you can think about it, a trick that kind of help you remember, you can treat this like you're multiplying both sides by dx, where the dx's cancel, and then you're left with that. So let's do an example. Let's say we have this. So we have d sine of some function u of x dx. Well, using the chain rule, we get the cosine of u, and then du dx, whatever function u happens to be. It could be x squared, it could be square root of x. And so that means we can think about this as if we were multiplying both sides by dx. And we would get d sine of u is cosine of u du. All right. So one thing to talk about next, let's take a look at estimating differentials. So one thing you can do here is we're looking for oftentimes the change in one variable. So the way this typically works is going to be this. Let's say we have this. we want to find the change in volume V. And let's say volume V is x cubed. So this is of a cube. When the edge lengths change from x0 to x0 plus dx. So what we're going to do, this is really a kind of approximation is what we're looking for. So the idea is going to be this. We know delta y, or delta f, is f of a plus dx minus f of a. And we can say also that df, the other change in f, is f prime of x dx. Now, the rule of thumb is going to be this. We're going to say that delta f and df, let's take a look. One thing. Sorry, I'm just looking at my notes. These are from a couple days ago. Just want to make sure that I agree still. Yes. So what we're going to say is this. Delta f is approximately df near, again, x equals a. So what we're going to do for this problem is that for us, going back to our volume, we have our volume of a cube is x cubed, and we're going to look at this near x. 0 is going to be our a. So we're going to say that df is about delta f. What we want is delta f, but we're going to approximate it with df. And again, this just makes life a little easier. So our volume is x cubed. dv dx is 3x squared, or dv is 3x squared dx. So again, this is going to be approximately the delta v, how much the volume changes when we increase the edges from x0 to x0 plus delta x, or dx. So what we're going to do is delta v is approximately dv near x equals a equals x0. So that means delta v is approximately dv, which will be 3 x0 squared dx, which is 3 x0 squared dx. So let's take a look at another one of these. And again, if you have any questions about these, let me know. Just send me a message. So the radius of a circle increases from 2 to 2.02. So what we're going to do is we're not going to find the change in area delta A exactly. We're going to estimate the change in area. So that means this change in area, we're going to look at it as approximately delta A equals approximately dA. So we're going to need dA. So the area of a circle is pi r squared dA dr is 2 pi r, or dA is 2 pi r dr. So this is what we're going to estimate delta A with. So R, in this case, the R is going to be the original 2, could be 2 feet, 2 centimeters, the original 2. So that's what our R is going to be. Now for dr, that's the difference between the new radius and the original radius, or 2/100ths. So what we'll get is that dA is going to be 2 pi times 2 times 0.02, or approximately 4.08 pi. So that's the approximate change. Now, to find what the approximate new area is, we'll take the area computed at this radius of 2 plus the change. So the area computed at 2 is pi r squared, or 2 squared, plus our dA, and that's going to come out to, let's see, just checking, just converging with my notes here. Oh, I'm sorry. This is 0 point. My apologies. Take a second to update your notes there. That's 0.08 pi, or 8/100ths times pi. And then for this one here, let me change this. This is where we get the 4.08 pi. So approximation for dA, approximate new area. So sorry about that. That's a 0.0, 0.0. The approximate new area, 4.08 pi. So how well is this approximate new area? Well, let's calculate the actual new area. So granted, this might seem a little circular, but we just want to see how well our approximations are doing. Well, again, this is going to be r is 2.02. So that means the area is pi 2.02 squared, or approximately 4.08, well, 4.0804 pi. So to find the error between the two, well, we have 4.0804 pi minus 0.08 pi, and that's actually pretty, there you go, 4/10,000ths times pi. So this is how far off our approximation was. Now, why would we want to be doing these approximations? Why not do something, just throw the formula in there? Approximation formulas, they're helpful, for example, in computer programming, when you have a lot of calculations, some very intensive calculations. For example, a square root can be a more intensive calculation, possibly, than, say, 1/2 times x plus 1, like we saw in one of our previous examples. But these linear approximations, they're just more processor friendly. And so if the error isn't going to be important, if it's not going to hurt your calculation, then what you can do is you can use these approximations to basically make your program run faster, run more efficient. So that brings up the question of areas, or errors rather, I'm sorry. So I'm going to go through, let's see. They do have an error formula, and I just want to go through the derivation of it. All right. So the error, it's the actual change, the delta F or the delta A or the delta V, minus the differential. Could be dF, dA, dV. And we use for the differential the f prime of x, or f prime of a, dx. And if you recall, we're letting dx be delta x. So delta f, that's the difference in f values. And again, since dx can be delta x, we're going to go f of a plus delta x minus f of a. That's your delta f. And then still subtract f prime delta x. Now, what we're going to do, be a little clever here, we're going to factor out a delta x. So we can treat this, and this is just a really neat trick. You'll see this a lot in calculus classes. It's a neat algebra trick. But we can treat this as delta x minus f prime a delta x. And again, this delta x would cancel with this one, and so they would disappear, and well, you have the original difference. But the reason we can write it like this is now we can factor out a delta x from both of these terms. And so what that's going to give us, and again, that's just kind of a slick algebra trick. One of those things that you just sort of learn in calculus. we're going to get something like this. And what's interesting about this is if you think about the derivative, f prime of a, to get this, if we had a limit here, the limit is delta x goes to 0. This becomes that. So we're going to approximate this with this. And so the approximation of this derivative, the difference between the approximation and the real thing, we're going to call that epsilon. So this whole thing, the derivative, its approximation, in other words, we took the limit away. The difference between the approximation and the real derivative, we're going to call that epsilon. So this means delta f minus df is equal to this epsilon delta x. And so if we solve for delta f, the actual change in our function is the differential change. And remember, df, this is the change of the linearization representing f. The actual change in the function is the change of the linearization plus an error term. And we're going to keep expanding this. This will be f prime of a dx delta x. And again, this is all near x equals a. So that's our df here. And of course, this is the estimation of the change. Differential is the estimate. And because it's an estimate, it's going to be a little bit off. And it's off by that error term. All right. Now, there's different types of computations they do here with error. And we're going to take a look at some of these. We're going to have what's called true change or true absolute change, estimated absolute change, and then the approximation of the error. So let's take a look at this. Another way you could think about this is that you can think of this as true value equals the estimated value plus an error term. That's another way of thinking about this. All right. So let's say find the approximate or the approximation error for f of x is 2x squared plus 4x minus 3. We want, this will be our a, x0 is going to be -1, and we have a dx, which is 0.1. Because again, when we're working with these differentials, the differential approximation df has a dx in it. So let's figure this out. Part A. We want to find the true absolute change. So the true absolute change. Well, what this is delta f. So we just want the change in the function f. So this means it'll be f of -1 plus 0.1 minus f of -1. And so if we compute this, and again, this is our function, we'll get, and I'll skip the arithmetic, but minus 4.998 minus -5, and this will be 0.0002. So that's the estimate, that's the actual delta F, that's the true change. So now we're going to do the estimate absolute change. So we found out the true change. And again, we want to see if our shortcut, if you will, if our estimate's going to be all right. So the estimate true change. Oh, I'm sorry. Estimate absolute change. Getting things confused. Well, for this, df is going to be f prime of a dx. Now, for this, if you take the derivative of this, you'll get f prime of x is 4x minus 4. Oh, sorry, plus 4. Plus 4. So that means df will be 4 times -1 plus 4, because that's our x0, times dx. And what you'll get from this is 0. So funnily enough, for the estimated absolute change is, well, there's no change, it's 0. Now let's take a look at the error. So the approximation error that's delta F minus our approximation, or 0.0002 minus 0, or 0.0002. So any questions about that, again, let me know, but that's going to be our error. So the last thing to mention in this section, it's what they call sensitivity to change. So there's a couple ways we're going to look at this. There's different ways of measuring this, and we're going to talk about, first off, what we call true change. And again, this is going to be the delta F. Now, what we're talking about here is how much does delta F change when the X value changes? So the absolute is delta F. Well, it's just the change in F. So again, what we're interested in how big is this going to change? How big is this when we go from this x value to this x value? That's what we're interested in. Now, another way of looking at this is relative. So how big is delta F? How much change are we looking at? Well, we'll compare delta F, make a ratio of delta F over F of A. And then we can do a little more work on this. We can do a percent. We take this ratio, we multiply by 100%. So that's, and this is something that comes up a lot in mathematics, actually. When there's a small change in the x value, like only a dx is added to our x value, you could get a big delta F. And that's what we mean sensitivity to change. As you go, what does delta F do as you go from x equals a to a plus delta x? Or to put another way, how big is delta F as a goes to a plus delta x? And if there's a big delta F, sensitive. Our function is sensitive near x equals a. And this can be actually kind of an interesting phenomenon, even be a little bit of a problem in some ways. So that's how we deal with the true change, the change in delta F. Likewise, we're going to ask the same questions about df. So we're going to look at the estimated change. And again, we were using our estimate. Maybe it's easier on our computer processor to use our program. It runs faster if we use an estimate, or it's just easier to compute if we can afford some error. And we're going to have the same three types. So there's absolute. And again, we use df equals f prime of a dx. And then relative, well, this will be df divided by f of a. Like we compared delta f to f of a, now df to f of a. And then finally percent. All right. So it's going to be the same idea. So what we're going to do is take a look at a couple examples. So the first example, and we're going to go through these calculations is what we're going to be doing. So f of x is x squared. We're going to have x equals a equals 2. And we're going to let dx be 0.01 or 1/100th or 100. So we're going to go through the different types of change here. We have our true change. And again, first off is absolute. So this is delta f. So delta f is x squared, so that's going to be x0 or a plus dx. And we square that, and we subtract a squared. Because again, this is x squared. And what this will come out to is this number. And just to kind of remind everybody, this will be a plus dx, and because this is x squared, this is squared minus a squared. And so that's where this is coming from. Now that we have this number, we can compute the relative change. And this is delta f, which we just computed, over f of a. Now f of a is 2. F is x squared, so f of a is going to be 2 squared. And so this will become this right here. And finally, for relative, or a percent, delta f, fa times 100%, or this number, I'll write it over here, and then we get not much of a change, about 1%. And so that's how we get those first 3 calculations for true change. So now we're going to look at estimate change. And so that means we're going to look at the differential. So to do that, we need the differential. So we know f of x is x squared. So df dx is 2x. So the differential is 2x dx. And we want to keep in mind our x equals a is 2, and our dx is 0.01 or 100th. So again, we're going to look at absolute, relative, and percent. So the absolute is just the computation of df, just like we did the computation of delta f. So 2 times x equals a, which is 2, times dx, 0.01, and that's going to come out to 0.04 or 400ths. So that's our absolute. That's our actual change. or estimated change in this case. Now for relative, this is going to be df over f of a, or 0.04 over 2 squared, and that'll come out to 0.01, or 1/100th. And then finally, percent change. It's df over f of a times 100%, or 0.01 times 100%. And so what we're going to get is 1%. And what's interesting, the estimate, we get 1% change. For the true, we had 1.0025% change. So these aren't too bad. Of course, it helps that our delta x is fairly small. That's going to help. We're looking at not too far from x equals a equals 2. So that does help. So just to kind of illustrate more sensitivity calculations, let's say we have this. Now, an issue with sensitivity, it's not just going to be dx, but it's also going to be where you choose your x value to begin with. It's not just dx. So let's say we bring this function in. And we're going to take a look at ds. We're going to take a look at ds at different values of t. So first off, let's find ds. Now, one thing we're going to do, we're going to let dt be 0.1 or 1/10. We're going to go with that for our dt. If we're dealing with ds, we're going to deal with dt. So ds dt is 32t, or ds is 32 dt. So we have our dt, we have our ds. So this is what we're going to do. We're fixing dt. Oh, I'm sorry, I forgot. Left out a t. T dt. So what we're going to do, dt is going to be the same, 0.1, but we're going to vary this. And what we're going to find is ds is going to have very different values depending on what we choose for t. So the choice of t is going to be another source of sensitivity, not just with dt. We can get sensitivity with t also. So at t equals 2 and dt equals 0.1, ds is 32 times 2 times 0.1 is 6.4. And then if we do the same calculation, but let's make t equal 5 and dt 0.1. So ds is 32 times 5 times 0.1, or 16. So the moral of the story is going to be this. You want to notice the change ds is sensitive to the time t even when dt is the same. And what this basically, the way you could kind of think about this, if you look back at this function, s of t is 16 t squared. When we think about this function, it's a parabola, and what it's basically saying is that as you use larger values of t for this particular function, the change in this function is going to get bigger and bigger. Like, for example, if you have maybe a more easier example to think of, let's say we have this. Let's go with f of x is x squared. If you look at f of 1, 1 squared is 1. F of 2, 2 squared is 4. So delta f is 3. So again, if we do the same thing, say f of 2 is 4, f of 3 is 9. So in this case, delta f is 5. Well, the same is going to be true with the differential. Where we choose our time t in this case, we're going to get bigger changes in ds, just like we can get bigger changes in delta f. So anyway, so that's it. If you have any questions, let me know. That's 3.11. And again, any questions, let me know. I'll be checking my email throughout the break. And other than that, have a great break. And again, the homework should be due on Sunday, so about a week from today. And other than that, let me know if you have any questions.